Hi everyone, thanks for attending my very first CLC talk, by the way. I'm here today to talk to you about wireless technology and especially about the implementation in the Linux kernel. So I am Alexis Lothoré. I work at a company named Bootlin. We are specialized in embedded Linux development and many software around the Linux kernel. And recently, I've been able to work on some wireless device related topics, especially around this small chip here, Wilk 1000, and a bit about around Wilk 3000, which has been upstreamed quite recently from Marek, who may be around. And this talk is about giving you some very introductory elements about how to start writing some device drivers, maybe tuning some existing device drivers, and where to look at in the Linux kernel. For this talk, I plan to give you this talk in 5 parts. I will try to keep it as small as possible, but I need to talk a bit about the standards, obviously. Then we will see how it is implemented in the Linux kernel, what is the official wireless stack, and how our wireless drivers integrate in there. And we will actually see some code, see what is the basic skeleton to write a device driver supporting a wireless device. Finally, we will see, of course, some tools to start playing with our new driver and possibly how to start debugging and analyzing any possible failure with our driver. So talking about the standards and the specifications, so Wi-Fi by itself is only a marketing name. There is a well-defined standard behind it, and this is the IEEE 802.11. This is not a fixed standard. It keeps being improved year after year. That's why we have different versions with different features, with the general goal of improving the performance of our wireless devices, like the range, robustness, and things like that. We are currently on Wi-Fi 7, which has been released last year, if I'm not wrong, and there are new standards under progress, which should be released later. About this standard, it occupies the 2 lowest layers in our network stack. It defines at the physical layer how we can use radio to emit Wi-Fi frames. So what is the way to access the medium? What are the bands I am supposed to use with my device? What is the modulation and things like that? And on the MAC layer, it defines the type of messages exchanged by my wireless devices. In this case, we have 3 types of messages that could be exchanged between devices, and all the procedures, algorithms to exchange messages on the network, to join the network and maintain the network. About those networks, there are different networks specified by 802.11. For this talk, I will focus on the very basic setup, meaning the one we have at home. For example, when you have a router delivered by your ISP, you are using an infrastructure network. In this case, you have multiple station devices joining a network through a specific station, which is called an access point. This is not the only way of building a Wi-Fi network. You can get rid of some access points depending on the network you are using, like ad hoc, mesh, peer-to-peer, and so on. But for this talk, we will focus on the very basic one, the one we are used to use day to day. About the hardware, it comes in a wide variety of shapes and features. Features because any piece of hardware does not support the same revision of the 802.11 standard. That's why when you buy some wireless device, it may support 802.11, B, G, N, AC, AX, and so on. But also because the interfaces to work with this device may be different. We can get PCI cards, USB dongles, bare modules to solder on our products, and so on. One thing that does not generally change between all those devices is that they depend on some firmware to run, but more on that later. About the implementation and the overall organization in the kernel, we have to distinguish between 2 categories of devices when we talk about those wireless devices. We have the FullMAC and the SoftMAC devices. The FullMAC devices are in charge of handling both the physical and MAC layer. There are pros and cons to this. The pros is that it is a kind of offload in the end, so we may expect some better performance from FullMAC devices. However, of course, they may be more complex, both at hardware level and possibly at firmware level. And also, if we have an issue, like a firmware bug, for example, it may be harder to patch it because we may depend on a closed source firmware provided by a vendor, and so we have to wait for this vendor to release the fix. On the other side, we have SoftMAC devices. In this case, our device, and so the driver, only handles the physical layer. The Mac layer is running in software in our kernel. This is a generic layer implemented in the kernel. In this case, we expect, on the contrary, a simpler hardware and possibly cheaper in this case. And if we have an issue in the Mac layer, we can fix it. It's kernel, we fix the bug, deploy our kernel again, and all the SoftMAC devices benefit from this fix. However, there is one consequence, and it is especially important for low-power platforms. Our Mac layer is running in software, so our overall wireless performance may start to be CPU-bound. This is especially important to know. If you are running an access point with plenty of stations connected, your Mac layer is running in software and depends on your CPU. In the end, we have plenty of SoftMAC and FullMAC drivers supported in the kernel currently, but we have way more SoftMAC devices. When possible, this is generally the go-to path to implement our device driver. If you want to take a look at all those drivers, they are in drivers net wireless in the kernel tree. Now that it is said, what about the overall stack? This is how the wireless stack look in Linux. If we start from the bottom, we have obviously our hardware. On top of that, I have either a SoftMAC or a FullMAC driver. If I have a SoftMAC, on top of this driver, I have the generic Mac 802.11 layer running in the kernel. So this one will be in charge of the Mac layer, crafting and parsing frames for 802.11, a bit of encryption, decryption, queue management, and everything specified by the Mac layer for 802.11. On top of this, we have the CFG 802.11 layer. This is the main framework to control our wireless devices, to control and configure. This is the interface with which we want to interact from user space, and to do so, we have a thin layer, which is netlink sockets and a specific family of netlink sockets, the 802.11 netlink family. Through this socket, our user space applications can interact through commands and receive events from the CFG 802.11 framework. On user space side, we can have either our own application written with libnl, for example, or some small generic open source daemons. You likely have, if you have a Linux desktop or laptop, some WPA supplicant training, possibly some host APD if you have an access point, and at a higher level, a network manager, conman, systemd, networkd, and so on. Before taking a look at some actual code, we have some more details to learn about. In the Linux model, we have to distinguish between the wireless device, which is the actual piece of hardware, and the interfaces we see, for example, when I type IP link on my workstation. The wireless device is represented by this Wi-Fi here, wireless Fi. This is the representation of my hardware. If I have two pieces of network chip, I will have two wireless Fi. On top of one wireless Fi, I may have 0, 1, or multiple virtual interfaces. And those virtual interfaces are what I see when I type IP link, this WLAN 0, WLAN 1, and so on. So we will have to deal with those different entities. By default, as a user, I expect to have at least one virtual interface created whenever my hardware is initialized. And as a user, I can add other interfaces on top of this same hardware. Now, let's take a look at some actual implementation detail. We will see how to write some small driver skeleton. The first thing we have to know is about the main data structure that we are going to manipulate. This is the struct wireless Fi. As the name suggests, this is really about describing the hardware and more specifically about my hardware capabilities. So whenever I will write a driver, either directly or indirectly, depending on SoftMAC or FullMAC driver, I will have to allocate this structure and to fill all the details about what my hardware is able to do. Is it able to act as a station, an access point, peer-to-peer, and so on? Is it able to have concurrent combinations of those interfaces? What bands it is expected to operate on, etc. On the right, for example, we have an enum that I will have to use to say, okay, my device is able to act only as a station. So to get actually this structure, We will start with SoftMAC driver, so the most common solutions that you will see in the kernel. You won't allocate directly this wireless PHY. It will be wrapped in some other structures, and so you will rather start by manipulating an IEEE 802.11 structure, IEEE 802.11 hardware structure. To get this one, you call this allocate hardware API. It will consume a set of operations, your driver operations, more on that later, and it will give to you in your driver this hardware structure. It is then up to you to complete this structure with your hardware capabilities. In there, inside the structure, you will have your wireless PHY. So that's where you will set your low-level capabilities and some additional flags, for example, to let the MAC 802.11 layer know about what it should handle or not, depending on your offload capabilities. Once you have filled your structure, you are ready to register it in the kernel. And from there, you pass back this hardware structure to the MAC 802.11 layer. It will register the wireless device and perform automatically some steps for you, like registering your first virtual interface. That's why when you insert your driver, you may have automatically your WLAN 0 interface created. All right, I have mentioned that I have some ops to define. You can take a look at the relevant structure, 802.11 ops in the MAC 802.11.h. You will see that there is a ton of operations. You don't need to implement all of those. It really depends on the features you want to implement and on the capabilities of your hardware. But you have a very minimal set of operations to implement. Otherwise, you won't even be able to register your hardware in the kernel. And those are those 8, I guess, operations. So you can start your wireless driver by implementing those 8. First, you have this add interface, remove interface pair. The MAC 802.11 core will call those operations in your driver to let you know that the user or the kernel wants to add a new wireless interface on top of your hardware. It is up to you here to register this virtual interface in a list, possibly notify the device firmware about this virtual interface if it needs it. But this one is really about the virtual interfaces being added or removed. On top of that, you also need at some point to know when to initialize your hardware. And to get this information, we have some start-stop methods to implement. Those start-stop methods will be called right before enabling the first virtual interface and right after disabling the last virtual interface. So that's a small window in which you are supposed to make your chip ready to operate, start listening to some frames that could be targeted to your device, and so on. And so we have this timeline in here with all the add and remove interface and the start-stop letting us initialize, deinitialize our hardware. So here we really distinguish between adding an interface and enabling it. All right, so that's half of those operations. Of course, the whole goal of this thing is to transmit frame. So I have a TX operation to implement. Here, this is a very basic version. The core, whenever it needs to send a frame on behalf of user space, will call this operation and provide an skbuf, the standard representation of a packet in the kernel. This is a push model, so really the core is pushing a frame to my driver. It is up to me to send the frame through the device and then notify asynchronously my upper layers about either the success or failure about this packet sending. In fact, this is not the only TX-related operation I have to implement. I also have this wake TXQ. In this case, this is rather a pull model. I still have to implement it. And in this case, the kernel, and so the MAC 802.11 core, is queuing some packets in a queue and is letting me know each time it queues a packet. And then it is up to me in the corresponding ops to either start dequeuing or manipulating the different MAC 802.11 queues to get the next packets. Through some specific APIs like TXDQ, NextTXQ, and so on. I do not need to provide my own implementation of this callback. If I want a very generic way of sending packets and dequeuing packets, I can directly use some default implementation in place of this wake TXQ. And in this case, I will have this whole timeline of packet sending on the right. Yeah, and so basically, default implementation will automatically call my TX operation. Okay, so that's it for sending. I'm still missing 2 operations. I have a small config operation to implement. This one will be called by the core each time it needs to reconfigure some low-level hardware detail on my device. Should it enable power save? Should it change some operating channels and things like that? So it will provide a bit mask of the elements to change and to update on my device. And I have this configure filter operation to implement. By default, I will move many receipt frames to the upper layers, but the kernel may not be interested in all the frames. So to save some processing time, it is able to set a filter to letting me know about the frame I should drop rather than pushing to the kernel. Okay, so we have the basic operation. We are still missing one important detail. This is about receiving frames and pushing those to the kernel. We have different APIs provided by the Mac 802.11 layer, all in the same family. So the basic one is the _RX, and very basically, I will take the received frame from my chip, put it in an SKB, and push it through this API. Of course, I will likely use this kind of API in an interrupt chain, because this is how my device will notify me about a new packet being present. And I have different versions depending on whether I want to handle some queuing in my driver, if I want to do it directly in the interrupt, and so on. In any case, there is one constraint about this family of API. I need to have an 802.11 header at the beginning of this SKB. This is what those APIs expect. Okay, so we have all the very basic building blocks of our driver. If I want to write a short skeleton, I will create this Mac 802.11 structure containing all my basic operation. Once again, this is a tiny subset of all available operations. And then in my driver initialization sequence, so in the prop function, I will start, for example, by preparing the receive path with some interrupt registering and work queue declaration. I will allocate my hardware structure, and then I will set some fields in there. I may have some MAC address to configure, to attach some strict device. I will have some flags to set. So this is what these hardware set APIs are doing here. So setting some rate control capabilities, some power save capabilities. And I will do it both on my hardware structure and the wireless PHY. I have to configure my wireless PHY. So for this basic example, I am saying I support both station and access point modes. And once I'm done, I will register my hardware structure. From this point, the kernel will know about my wireless device, and since it is a SoftMAC driver, the Mac layer will automatically register and expose to user space my WLAN 0. Just a short part about the RX path, assuming that our packets are received through an interrupt. I don't want to deal with the packet management directly into the interrupt. I want to defer it in some bottom half. So this is the second function. And in the second function, I will retrieve my packet, prepare it into an skbuf, so this struct skbuf skb, and push it to the kernel. So that's how I will transmit the received packets to the user space, or the kernel, the Mac 802 layer, if it needs it. So that's pretty much it for the SoftMAC drivers, which covers a large part of available devices on the market. But sometimes I have some FullMAC drivers. That's in fact the case for the drivers I've been working on, the Wilk 1000. And in this case, I don't have Mac 802.11 anymore, so I have plenty of things to handle on my own that were done by this layer before. So for example, instead of declaring some IEEE 802.11 ops structure, I will declare directly some CFG 802.11 ops structure. I won't have my wrapped hardware structure. I will directly manipulate and allocate, this time, my Wi-Fi structure. On top of that, I will have some new structures that I will have to manipulate. That was not really mentioned in the previous slide, but whenever the Mac 802.11 layer calls my driver, it provides some specific VIF structure. I won't have this anymore. Here, I will have a lower level structure, which is a wireless dev. This represents my wireless virtual interfaces at the lower level. Another important thing, I don't have Mac 802.11 anymore, so I have to register on my own the StructNet device. So not only I need to perform the wireless PHY registration, I also need to register a StructNet device if I want to have a default interface. And each time a user wants to add a new virtual interface, I will add to do it as well. This is important because I need to enforce the link between those net devices and the wireless, the virtual interfaces. And that's done through a specific pointer inside my net device structure. So I will have to remember to properly set this pointer in my driver each time I want to add a virtual interface. Once again, I have some operations to implement. There is, once again, a lot of them, many more than in the Mac layer. And once again, I don't need to implement all of those. Some are very specific to some non-standard features. I don't have a strict set of mandatory features to implement. The CFG layer won't refuse registration because you are missing an operation. You will just have some specific kernel errors at runtime when the user will try to call some specific ops. But as a starter, if you want to implement a very basic station, you can, for example, count on those operations and implement those. Some will be similar to what we have seen for the Mac layer. So I will have some add virtual interface, delete virtual interface. That's where I will have to register the virtual interface, but also register the net device that matches it. I will have to implement some scan features. So that's how the user space will ask to learn about all the surrounding access points. Some connect-disconnect procedure, with which I will receive information about what access point I want to connect, and some more specific key management operations that will be used, for example, by a user space supplicant. More on that in a few slides. As discussed earlier, I need to register a net device, and so I need to declare some net device operations. Once again, I don't need a very wide set. It really depends on the features I want to implement. But here you need at least the features that were implemented by the Mac 802 layer when you implemented the Mac 802.11 ops. So for example, I need some open and stop ops that will be called whenever I bring up or down my virtual interface. And I need an operation to be able to send packets. So I need the NDO start XMIT. On the receive side, I don't have some CFG 802.11 specific APIs. I will directly use the standard NetStack receive APIs, so some native RX or an AP0 receive if my driver implements an API loop. Of course, I have some exceptions. Whenever the upper layers subscribe to some specific 802.11 frames, I will have some specific callbacks to push those frames up to the upper layers. So I don't have any skeleton for FullMAC drivers. Here the main point is about remembering about this StructNet device, and specifically to remember about this small pointer to link to a wireless dev inside the structure. However, we can discuss a few additional outstanding features, let's say, that we should consider when writing wireless drivers. First of all, I have mentioned in the first slide that we need a firmware running on our device to operate it. This firmware is, of course, not part of your driver. It is out of your driver. It is out of the kernel, in fact. Most of them are hosted in a standard Linux repository on kernel.org, the Linux firmware repository. So it is up to you as a user, as a developer, to make sure that the firmware you need is present in this repository, and as a user to install it on your system. You generally expect those firmwares to be present in lib firmware, and your driver will request, when relevant, this firmware with the request firmware API. So it is up to your driver to find this firmware, request it, and load it into your device at the relevant point of time during your device lifetime. I will get back to it later, but you are not supposed to load this firmware right at prop time, but maybe in the start operation in your driver. A word about key management and connection in general. By default, your driver and the wireless subsystem in the kernel overall is not really able to handle by itself the standard ways of connecting to an access point today. It supports some open networks and some web network, but please don't use it at home. You rather should use some WPA2, WPA3, some more modern standards to connect to your access point. This is not supported by the kernel. This is deferred to user space. So you need a supplicant on user space side to handle all those operations. There are some handshakes to perform, which will negotiate some cryptographic keys to encrypt the traffic and so on. And so this is deferred to user space. So there will be multiple netlink 802.11 messages exchanged between these user space components and the kernel and or your driver. This is important to know because at driver level, depending on your device, depending on its firmware, it may be able to handle more than the basic operation. So for example, being able to handle the whole WPA handshake. In this case, you want to let the wireless core know about this because you don't want it to make all the back and forth with the user space. So how is it done? You have your wireless file structure. At initialization and registration, you will make sure to set the relevant flag to let the core know about this capability. And then, once the user space initiates the connection, it will just wait for your device to finalize and return the status of this connection. A word about regulatory. Whenever you are using a radio device, and I think that's not only true for Wi-Fi, you are expected to respect some regulations. You cannot use any transmit power, you cannot use any radio bands as you want. So you have some regulations to respect. And the overall goal of this framework is to make sure that the user cannot accidentally fail to comply with those rules. So we have some mechanisms to try to enforce correctly the relevant rules. All those rules are not registered in the kernel, once again. This is hosted in a dedicated repository in the wireless RecDB. And we have this half-textual format listing all the known rules for any supported country. Here we have an example of the regulation in Netherlands. I can use my wireless device in the 2.4 GHz with a transmit power up to 100 milliwatts. So this is some textual data. It can be turned into a binary, so I will have to install this regulatory.db file into my system. And at init time, when the CFG 802.11 core initializes itself, it will search for this file to load all the known rules. It won't be able to apply yet a specific set of rules because it does not know yet what regulatory it should apply. So it will apply this world regulatory, which is a generic one, while we don't know yet how to apply the regulatory. From user space, I can enforce a specific regulatory. So here we are using IW to set the Netherlands regulatory. From there, my core will be able to configure any wireless file registered in the kernel with those rules, thanks, for example, to the config ops we have implemented earlier. Once again, at driver level, you may be interested in the customizations that you can do at regulatory level. First of all, you don't have to do anything for this. As I have mentioned, the config callback could be called to set your TX power automatically by the core. But in some cases, you want to know when the regulatory is changed. So you can subscribe with this reg notifier callback in your wireless file to know when the regulatory change. And so you could perform some checks, for example, compared to some data you may have in a non-volatile memory. You can go further. Maybe your driver somehow is able to guess about what should be the current regulatory because it has received the info from the firmware, which is processing beacons from access point, for example, because you have an EEPROM containing the information from some previous connections or things like that. So you have this regulatory hint, which allows you to notify the core about what you think should be the current regulatory. And more than that, you can also tune whether the core should be enforcing some regulatory to you because you cannot comply with any regulatory or because you know that you have stricter regulatory and you don't want those to be overridden by the core wireless system. So you have, once again, some flags that you can set at registration time. But in any case, once again, the overall goal of this is to make sure for the user not to fail to comply without knowing it with those regulations. So if you start tuning those regulatory, make sure that you cannot make the user emit with too much power, for example. Okay, one last consideration. If we discuss a bit of power save, the 802.11 standard specifies that our station devices can enter some inactivity period, let's say sleep period, in which during which it will not be able to receive and transmit frames. There is a well-defined mechanism for this, during which the station will notify the access point about this period, sending a null frame. And from there, the access point will remember about the sleeping station. And if there is a frame targeted to my sleeping station, it will be buffered on the access point side. And the access point will start emitting, will modify the beacon it periodically emits to notify about those pending frames. From time to time, my station will wake up, listen for the beacons, and check if there is a pending message for it. If so, there is another well-defined message to ask the access point to dequeue those pending messages and to send it. So this is this PS4 frame. Once again, this is a feature which is pretty well supported with the SoftMAC layer. I still have to let the core know about the fact that I can support this feature. So we have yet another flag to set this time in the hardware structure. And after that, so the core will consider that I am compatible with this sleep mode. I will either still have to deal with some specific frames, like sending the null frames whenever I enter or leave those sleep periods, or I can defer some of this work to the Mac 802.11 layer. So once again, plenty of flags to set at registration time. For the FullMAC driver, we consider that you will handle it on your own. So the only thing you can implement here is the set power MGMT ops, which will be called whenever the user enable or disable power save. And then it's up to you to handle everything. Talking about the user about this power save, he is able to toggle it with IW again. So here we enable power save on a specific virtual interface. And it is worth mentioning, especially for early development, because even if you do not call this command line, power save may be enabled on your station for multiple reasons. Maybe because your drivers has registered the device telling, don't worry, you can enable power save by default, or because the kernel is built with this specific kconfig. And it is pretty important to know about it because it can be quite painful to start debugging an issue for multiple hours and realize that, in fact, your chip has been sleeping and possibly having a bug in the firmware during the sleep and things like that. So that's likely something that you want to make sure to disable during early development and deal with it later in a second step. All right, just a few design tips. Those tips are not really related to wireless drivers. They could be extended to any device driver, but that's what I feel is relevant for this topic. First, your hardware does not need to be initialized right at probe time. And that's generally what the wireless maintainers will ask you whenever you submit a new driver. You should keep it off as long as possible. And what is as long as possible? As long as the user does not need it. That's why you have all those start-stop ops implemented. That's a good place where to start actually loading a firmware, for example. That's where you will start listening for the interrupt about received messages. But as long as the interface is done, as long possibly as you don't have any virtual interface on top of your wireless Wi-Fi, you don't need to make the firmware run and initialize all the hardware. About the registration order, once again, make sure to have properly initialize all the fields in your data structure before passing those to the kernel. Because as soon as you register your hardware structure or your wireless Wi-Fi, the kernel can immediately start calling your driver ops. With Mac 802.11, there's not much room for mistakes, let's say, because there is only one set of registration API. But for FullMAC, you have both the wireless Wi-Fi to register and the net device. So you can start making mistakes here if you are not careful about proper initialization before registration. If you have a wireless chip, there's a high chance that you have different revisions of the chip, different buses that you can use to address the chip. Of course, you are expected not to duplicate the code between those chips. You should keep the matters separated. For example, if you have a card which supports, I don't know, SDIO and UART to work, you should likely create some SDIO and UART dedicated files and keep your wireless operation in a single set of files shared between those two buses. But once again, this is not really wireless specific. And finally, don't be scared by the amount of things to implement. If you take a look at the MAC 802.11 header and CFG 802.11 header, you will see lines and lines of operations to implement. You don't need to start implementing all of those. I've given to you here the very minimal set you may start with, and you do not even need to implement those. Just start by stubbing those, generate some logs from those, return some standard success code, just to learn how they will be called by the core depending on what user space action is triggered. All right, let's finish this tool by checking how to actually test our new fancy driver. About the user space tools, the first one I could use to start playing with my driver is IW. This is a standard user space tool which communicates through the netlink socket we have discussed earlier. This is a command line interface coming with many subcommands. So for example, I can learn about all the wireless files registered in the kernel, and I will have all the list of capabilities. So for example, I can check whether I have forgotten about a specific flag at registration. I can start manipulating my virtual interfaces. So here I add a WLAN 1, which will act as a station. That's what the managed flag means here. And I can possibly start playing with some connection and scan. So here, triggering a scan, connecting to a simple network. Once again, this is not WPA2 or 3 here. This is web, likely. I can take a look at the connection status, and I can also start performing some very early debug. So for example, I can ask EW to let me know about any netlink 802.11 events notified by the kernel. So to see the overall timeline of messages exchanged between user space and kernel. If I want to go further, I will likely want to check that I can connect to standard networks. And in this case, I will need a supplicant. I have different solutions. The standard one in the Linux ecosystem is WPA supplicant. It comes both as a daemon and a command line tool, and in fact, a library to write your own tools. And you have some other alternatives. There is IWD, which is a more recent from Intel, I guess. And to start using it, it is really straightforward. I have a very minimal configuration file to write, only those 2 lines, and I think the second one is not even needed. I will have to start my WPA supplicant daemon. I provide the kernel interface it should use, the network interface it should operate on, and the configuration. And then I can start using WPA CLI to initiate the scan, spot the network on which I want to connect, configure the credentials, and initiate the connection. And with only those operations, I can start checking that the written driver behaves correctly and interacts correctly with my hardware. Last word about debugging. First of all, there is many debug logs in both CFG 802.11 core and MAC 802.11 core. So I have to take care about building those at build time, so making sure that they are embedded in my kernel image and module files. But then at runtime, I can use the dynamic debug entries to enable those messages. On top of that, I also have plenty of trace points. So if you are familiar with ftrace and tracecmd, you can enable those trace points. And those are very useful because you will see all those drv underscore something. Those are the entry point and exit points where the kernel is actually calling your driver operations. So you can make sure what exact execution path trigger your driver. Finally, at some point, you may be interested in packet contents and making sure that your driver emits the correct packets. You can use another device, like your development laptop, raise a monitor interface onto it with the add-a command we have seen earlier. You will bring it up, possibly configure it to listen on a specific channel on which you are performing your tests, and then use some TCP dump. And from there, you will be able to see all the 802.11 frames exchanged between your device under test and an access point, for example. So here, I am tracing a whole connection sequence between a device and an access point. Of course, if I can do this in TCP/dump, I can do it in Wireshark. And that's even nicer because there I will be able to analyze the detail of every packet generated by my device or received by my device. All right, that's pretty much it about what I wanted to show you. Just a few additional resources. This was really a high-level quick start of how to write the driver. If you want to go further, there is a nice official Linux wireless documentation. This is a dedicated website where the maintainers and the main developers of the wireless subsystem have put some notes, some discussions and reasons about implementation. So a very good source of information. You have access to the 802.11 standards. The most recent versions are paying documents, but you don't need the most recent versions unless you are implementing some very bleeding edge features. So the older versions are available for free. And finally, of course, you have access to all the community code and documentation. You have access to the mailing list and the drivers in Drivers.net Wireless. So that's all for me. I hope you will have learned a few tips about the device driver. And if we have a bit of time, I would be glad to try to answer your questions. Thank you. Yes?
Very nice work.
Thank you.
And I've done some work with some wired Ethernet drivers. So obviously DMA transfer is a part of the thing when doing TXRX. Is it similar with wireless?
So the question is, compared to Ethernet development, where we may have some DMA management at driver level, is there the same concerns on the wireless part? So yes, of course, it is up to you to configure. You will have some DMA, for example, on the bus you are using. You may have some DMA on the controller interfacing your device. And of course, that's a matter you have to address in your driver. Once again, if you are writing the basic skeleton of your driver, you maybe don't need to start writing DMA management at the beginning. You can start with a basic operation. But yeah, that's the same concern.
Are there any other differences between wired and...
Oh, is there any other difference between wired and wireless drivers? I would say yes. I have no clear picture in my mind. That's a very wide question. From my point of view, the testing seems a bit harder because you will have to deal with some uncertainties, let's say, when you are testing wireless, some lost packets, some radio performance, and you may suffer a bit less from it with Ethernet. But then you have a whole variety of details that are, of course, specific to Wi-Fi. The nice thing, however, is that you clearly see that there has been a lot of efforts in the core subsystem in CFG 802.11, in MAC 802.11, to make sure that not all drivers replicate custom behavior in there. So you have some generic frameworks, even for the most specific features that your device may support. Yes?
Yeah, maybe just to expand on the debugging tools. I find personally that instead of TCP/dump, sometimes using arrow-dump is a bit nicer because you can have more control over wireless specific things like on which channel you're listening for packets. And it also generates files that you can read in a Wireshark.
Okay, and the solution was arrow-dump? Is it part of AirCrack? Yeah. So indeed, that's a nice suite to perform testing, and especially because this one will automatically perform the virtual interface bring up, I guess, the channel configuration. Yeah. So indeed, it's very nice if you want to go straight forward to the final testing direction. Here, the goal was really to give you the lowest level commands to perform your testing, to bring manually your interface. But of course, yes, you have some ways to automatically bring this setup as a whole. Yes? Sorry, could you try to speak higher? Loud. Okay, so the question is there is any tool to analyze the netlink packets exchange between user space and kernel? So there is one basic way to do it. Similarly to what we have done with the monitor interface, you can bring up a virtual netlink monitor interface, which is not related to the wireless subsystem, by the way. So you will do some IP link, add something. Well, you will use the IP route util to bring up a netlink monitor interface, and then you will be able to start either TCP dump or Wireshark on this netlink interface. And if you start Wireshark contains all the dissectors needed to parse the content of those netlink messages. So you have some debug tools indeed. Yes?
Do you have a good recommendation for modern Wi-Fi chipsets with good documentation, especially open one?
Wow, that's a big Christmas list. To be honest, no, I don't have such a recommendation. My work was quite focused on specific chips. Here, my best suggestion would be to take a look at either the mailing list and or the Git history in drivers.net wireless. If there is activity in here, and possibly in the Linux firmware directory as well, which would prove that the vendor is active as well, that would be a good hint that the device and the corresponding driver is in good shape. Yes, maybe one last question?
Any direction on how to debug reboot issues? I've been working on developing some drivers for a Wi-Fi device which just keeps rebooting after every 5-6 hours. And I can't figure out what that is about. So any tips on that?
So the question is there any tip about debugging devices that may reboot sporadically, right? If you are lucky, you may have some additional debug interfaces on your chip. So you have the main bus to start interacting with your chip, and possibly, depending on the interface brought by this chip, depending on the firmware running inside the chip, you may have, for example, if you are lucky, 2 small UART pins available to on which the firmware inside the wireless chip is outputting some logs. That could be one solution to try to identify those reboots. But honestly, that will always be a difficult topic, because here we are talking about a reboot inside the chip, which depends on some binary blob provided by the vendor, so you are a bit clueless. If the bug is on the driver side in the kernel, you have all the tools to investigate it, but that will be always more difficult on the device side. However, so there is a topic about debugging it, but the topic about handling those reboots is a known concern in the Mac 8.02.11 layer. So you have some ops that you can implement, which acts like last resort. You know that your driver has, your firmware has crashed for some reason. The core may be able to be notified about this. Your driver is telling to the core, I don't know in which state I am. And so you can implement some ops so the core can restart and reinitialize properly your device. So you have some fallbacks that you can implement in this case. All right, so thank you all.